So I wanted to recap some things we discussed in class. We talked about the solution to this equation, x squared plus 1 equals 0. We subtract 1 from both sides, we get x squared equals negative 1, and we're almost done. All we have to do is take the square root. And typically, up until this point, this is when we would stop. We get the square root of negative 1, and we say, oh, no real solutions. Well, that's not false. There aren't any real numbered solutions. What we do get is this complex number, I, which we define as the square root of negative 1. And so now we get a whole new set of numbers called imaginary numbers that lead to complex numbers. Now, one relationship that's important to note is that the square root of negative 1 is equal to I. So if we were to square both sides, we get that negative 1 is equal to I squared. Now, any complex number is defined as something that has the form a plus bi, where a and b are real numbers. And in here, in this number of this form, we've got a is the real part, and then the bi in its entirety is called the imaginary part. And we've got some examples below. We've got 5 plus 3i, 1/3 minus 6i, 5i, and 1/2. Now for the 5i, this is still a complex number where we understand that the real part is 0. And for the 1/2, this is also a complex number where the imaginary part is 0i. So let's look at some facts about complex numbers. We say that two complex numbers are equal if their real parts are equal and if their imaginary parts are equal. So that makes sense. When we add complex numbers, we add their real parts and the coefficients, so to speak, of the I terms for the imaginary part. And when we multiply complex numbers, we multiply it out by FOILing. And so we talked about this, and the one thing you need to note when you're FOILing is that when we get I squared, that's going to be equivalent to negative 1. So we'll want to make that substitution accordingly. But I don't expect you to use this formula when you're multiplying. I expect you to just FOIL it out. So I wrote a couple of examples here. Once again, I'm not going to go through them in strict detail just because we already did in class. But when I when I add 2 minus 3i and negative 1 plus 5i, what I'm doing is I'm adding the real parts. So 2 minus 1 is 1. And then when I talk about the imaginary parts, I got a negative 3i plus a 5i. So that just gives me a negative 2i. And actually, that should be a positive 2. So I'm glad I decided to go back over this. And now if I look at the product, what I'm doing is FOILing it out. So what I wrote down was what I would get in that process. So I have my first two terms, my outer terms, my inner terms, and my last two terms. And then what I did was simplify. Note that once again, I'm using this fact that I squared is equal to negative 1 when I jump from this step to this step. And then I just end up simplifying by combining the real part, so negative 2 plus 15, and then I still have that imaginary part, 13i. So let's talk about plotting complex numbers. So if I've got 4 plus 2i, have this coordinate system, I'm going to label this as the real axis, and this is the imaginary axis. So in this number, 4 is the real part, which means I'm going to go over 4 on the real axis. And then 2 is the imaginary part, so I'm going to go up 2 on the imaginary axis to plot z1. Now if I'm plotting z2, I have that that's negative 3i, and so all I'm going to do is go down 3 on the imaginary axis, and that's going to give me z2. For z3 equals 5, well, there is no imaginary part, so I'm going to go over 5 on the real axis, and I'm just going to stay there because I don't go up or down. There's no imaginary part, so this would be z3. Now, the second part of this example says, find the modulus and argument of z1. Well, what is a modulus? What is an argument? So one thing that's important to note is that if we start at z1, draw a line to the origin, then if we let that be the terminal side of this angle theta, we get an angle that's created between this terminal side and the real axis. And we get a distance, which we'll call r, and that distance is called the modulus. So our angle we call the argument, and the distance we call the modulus. And so how do we find this? Well, we've done this before plenty of times. This distance is 4, this distance is 2. So the modulus, which we usually sometimes write with absolute value sign of z1, is going to be the square root, using Pythagorean theorem, of 4 squared plus 2 squared, and that's going to be the square root of 20. And our argument, theta, is going to be, let's see, I'm going to run out of space if I write argument. So we've got that theta, the tangent of theta, is equal to 2 over 4, which is equal to 1/2. So what we're looking for, we say that theta is the tangent inverse of 1/2. Now this isn't a special angle from the unit circle. We just need to use our calculator, and we're going to get that theta equals 26.6 degrees. And so this theta is called the argument once again. And this square root of 20 is called the modulus. Okay, so let's talk about the polar form of complex numbers. We have talked about them so far, like they're in rectangular form. So if we just have a general complex number of the form x plus yi, and we draw a line from that point to the origin, then we get an angle theta. And so just like when we were talking about rectangular coordinates, we can also rewrite those coordinates completely determined by distance r and an angle theta. And that same thing holds true for complex numbers. So we know that this distance here is y, this distance here is x. And so up to this point, we can say the same thing. We know that x is equal to r cosine of theta, and we know that y is equal to r sine of theta. So if we are rewriting our complex number z, we get that z is equal to x plus yi, but if we substitute, we get that that's equal to r cosine of theta plus r sine of theta I. And now notice we can factor an r out of both of these terms, and I'm going to move the I in front of the sine theta here. And we get a way to rewrite this complex number in a way that's completely determined by this angle theta and this distance r. Now, if you recall in class, we talked about a formula called Euler's formula. So Euler's formula says the following. It says that e to the I theta is equal to cosine of theta plus I sine of theta. And so if we think about that and we look back up at the above, we can substitute this cosine theta for an ei to the theta using Euler's formula. And so we get that if we're writing a complex number in polar form, instead of writing it x plus y to the I, we're going to write it as re to the I theta, where r is the modulus, or the distance from that point to the origin, and then theta is the angle that is created. Okay, so let's talk about a couple things with complex numbers. We want to talk about how to multiply and divide things in polar form. So let z1 equal r1 e to the I theta 1, and z2 equal r2 e to the I theta 2. So if we want to multiply z1 and z2, we get the following. We get that z1 times z2 is equal to r1 r2 e to the I theta 1 plus theta 2. So what we did was we added the exponents because we're using multiplication. Now if we're trying to divide z1 and z2, then we're going to get that's equal to r1 e to the I theta 1 over r2 e to the I theta 2. And we subtract exponents whenever we're dividing. So we still have r1 divided by r2, but since we have the same base here in e, we subtract the exponents. So we get I times theta 1 minus theta 2. So let's see these rules in action. Consider once again z1 equals 4 plus 2i and z2 equals negative 3i. If we plot them, recall we go over 4 up 2 for z1, and we go down 3 for z2. Now we want to write them in polar form, which means we want to rewrite z1 and z2 of something of the form r e to the I theta. Now we've already talked about how we could convert z1 to polar form. We have that z1 equals r1 e to the I theta 1, And if you recall from the last slide, this r here was the square root of 20. And the theta here was a 26.6 degrees. So this is how we would write Z1 in polar form. And what about Z2? We didn't talk about the modulus or the argument there. So if we look to get to Z2, we have to go down. This is an angle that's negative pi over 2 radians. So that's going to be our argument. And then what's our modulus? Well, this distance here is negative 3. You know, at this point, we're at negative 3I. So we can rewrite Z2 in polar form as R2e to the I theta 2. And so our argument here, our modulus is 3. And our argument is negative pi over 2. So this is how we would write both of these complex numbers in polar form, starting with them in rectangular form. And now I want to do some division. So how do we divide these two numbers? Well, if you recall, we need to subtract the exponents when we're actually doing our simplification using the exponent rules. So let's write it out first. So we've got Z1 divided by Z2. That's going to be square root of 20 e to the 26.6 degrees I over 3 e to the negative pi over 2I. Well, I can't subtract degrees from radians, so let me go ahead and convert. So I'm going to change this to square root of 20 e to the 26.6 degrees I. And on the bottom, I'm going to change this to 3e to the negative 90 degrees I. So here we go. First thing I do is just divide the coefficients for each of these terms. And then, since we have the same base e, I'm going to take 26.6 degrees minus 90 degrees. And in total, or finally, that's going to give me negative 63.4. I. So this would be the quotient of these two complex numbers in polar form. Now I want to find the product. To find the product, I'm going to multiply them together. So I've got the square root of 20 e to the 26.6 degrees I times 3 e to the, I'm going to go ahead and write in negative as negative 90 degrees I. So I multiply the constant terms. I multiply the r, so 3 square root of 20. And then I'm going to get e to the 26.6 degrees plus a negative 90. And ooh, it looks like I made a mistake up above. So I was subtracting the negative 90. I was subtracting 90 before, but I'm subtracting a negative 90. So if I go back up, this should be minus a negative 90. Right here, so this is going to become a plus 90. So that's going to change from 26.6 plus 90. And so instead of having a negative 63.4, I'm going to have 116.6. So good save. Hopefully one of you out there was saying something to the computer screen. I heard you all the way here in Pella, and I have fixed the problem. Okay, so let's get back where we were. We want to multiply Z1 and Z2, so we are at the point where we are adding the exponents, and 26.6 plus a negative 90 is going to be the same thing. It's going to be a negative 63.4 degrees I. So we've rewritten, we've not rewritten. We've written the product of these two complex numbers in polar form and their quotient, and we started off with them in rectangular form. So this is how you do these types of problems.